We're going to review what we talked about net force last time, okay? And we're going to start with a couple problems to review net force. When we find our net force, remember we take either rightward forces minus leftward forces, or we take up forces minus down. Do we remember that a little bit? Okay, that's going to be our goal for today. We're going to talk about the weight force. We're going to start looking at vertical things too, but we're going to kind of start putting it all together. It's important for you to remember that in this chapter, we're dealing with either horizontal or vertical forces. We're not mixing them yet. So make sure that you're careful to keep horizontal forces separate from vertical. Okay? So in this one, we're going to do a horizontal review problem here. Okay, so go ahead and get written down what you need to, and then we'll start working together to build our diagram and to finish what's happening here, okay? So go ahead and get written down what you need, and we'll start looking at our variables here pretty soon. Okay, so let's go ahead and look at our free body diagram here in this particular problem. How many forces do we have acting on our system here? We have two forces, one from the right and one from the left. Okay, so do we want Sam pulls with 16 newtons, do we want his force to be to the right or to the left? Okay, left. Doesn't make a difference. So I'm going to label that F sub S for Sam. F sub A for Andy. Okay, so we're going to start looking at now our net force equation. F net is equal to rightward forces minus leftward forces. So what would my equation look like? F net equals, good, F sub A minus F sub S. Okay, getting this equation and getting your free body diagram down are going to be your keys to success for these problems. Okay, first of all, we've got to think, is this system moving horizontally or is it moving vertically? Which one? Horizontal or vertical? Horizontal. So we really only are concerned with our horizontal forces here. Okay, so for chapter 4, we're only dealing with one dimensional. So we're looking at either horizontal or either vertical. Once we move to chapter 5, we'll start mixing the two. But for right now, we're dealing only horizontal or only vertical. So this system is only moving horizontally, which means we're only looking at our horizontal forces. Okay, we still always break down our net force equation into horizontal and vertical. So let's go ahead and start assigning some values and doing some substitutions here in this equation. We know that Sam's force is equal to 16 newtons. Okay, so we can plug in 16 into our equation, right? Because that's what F sub S is equal to, 16. We're solving for the force that Andy's pulling with. So we're going to solve for F sub A, which means that needs to stay the same in its equation. What do we know about F net? What do we know F net is equal to? Good. Mass times acceleration. Very good. M times A. This mass times acceleration gets substituted in for F net very, very, very often. Okay, whenever we see F net here, we can substitute mass times acceleration in there. Okay, so now we've got a few different variables. Do we have some variables that we can plug in? Do we know the mass of our system? Yes, we do. A 0.75 kilograms. Do we know the acceleration of our system? Okay, is our acceleration going to be positive or negative? Why negative? It's going away from him, but which direction did we choose his force to go? We chose his force to be negative, which means the acceleration would be positive. Okay, so here we're going to plug in a positive 1.75. If we had chosen his force to go to the right, then our acceleration would be negative. Okay? So how do we get F sub A by itself? Oops, you can't really see that. We're going to add 16 over to that other side. So add 16, which gives us 17.31 equals F sub A. Okay, so Andy is applying a force of 17.31 newtons. Okay, what if I asked for just the net force in this problem? What could I do? If I just asked for the net force of this system, what could I do to solve for the net force? Yeah, I would just take the mass of it times the acceleration. Whatever acceleration is given to you, that's going to be your net acceleration. That's the overall acceleration of the system. So that's going to be used to plug into your F net. Okay, your net force is your overall acceleration times your overall mass. Okay, so here's Andy's force. Is it greater than or less than Sam's force? It's greater than. Is the acceleration in Andy's direction or Sam's direction? Andy's, right? Since Andy's force was greater, the acceleration should go in his direction. Does that make sense conceptually? Right? He's pulling with greater force, which means the system's going to move in his direction. Okay? All right, and what should our vectors, should these two vectors be drawn equal to each other, one longer than each other, one shorter? What do you think? FA needs to be slightly longer. Okay, and I don't know that I necessarily drew it that way, but F sub A would be slightly longer. And you don't necessarily know that going into the problem, but after the problem you can look back and see if I want to fix my free body diagram, F sub A should be a little bit longer. Okay? Any questions on that? All right, let's try another quick example here. I apply a force of 20 newtons on a crate to the right against 15 newtons of friction. If the crate has a mass of 30 kilograms, what's the acceleration of the crate? So go ahead and get written down what you need to, and then we'll start looking at our free body diagram here. Okay, friction, in which direction does friction go?
Left.
To the left, good. Okay, force of friction. Okay, what about, Cole, can you give me another force?
Applied.
Okay, and applied goes which direction?
Right.
Right. Should it be longer or shorter than our frictional force?
Longer.
Longer, good. Explain why it should be longer.
Because there's more newtons of force.
Good. More newtons of force to the right. Good. Okay, Bree, can you give me another force?
It would be the normal force.
Okay, and which direction does that go?
Up.
Up. Very good. Normal force. And our last one, Elena, give me your last one.
The gravity.
Gravity, good. F sub G, very good. All right, very nice. There's our free body diagram for that. So first and foremost, I'm pushing to the right and we're asking for acceleration. Are we looking at horizontal forces here or vertical forces? What do we think? Horizontal, right? I'm not lifting the box. It's not moving at all. So the net vertical force here would be 0, right? If I asked for the net force in the vertical direction, it would just be 0 because it's not moving in the vertical direction at all. It's just moving left to right. So our vertical net force here would just be 0. Does that make sense? Okay, so if I'm asking for acceleration, I'm obviously not asking for vertical acceleration. I'm looking for horizontal acceleration. So let's go ahead and start looking at our net force equation in the horizontal direction. Okay, F sub net. And you could even label F sub net X if you want. X telling us it's the horizontal direction. Y would tell us it's the vertical direction. You can add that subscript if you want to help you differentiate, okay, I'm looking at horizontal forces here. Okay, that's up to you. So we're going to take our rightward forces minus left, which means we would take F applied minus what? Minus what force? Good. Force of friction. Now we can go back and plug in our numbers here. So F net is equal to force applied, which is 20, minus force of friction, which is 15. What can we substitute in for F net? M times A. Okay, M times A. We're solving here for acceleration, so A needs to stay the same. What's the mass of our system? 30. So we're going to say 30 times A is equal to 5 newtons. So if we take 5 divided by 30, that's going to give us a value for our acceleration of 0.167. And what's our units for acceleration?
Meters per second squared.
Very good, meters per second squared. So we're going to talk about a couple of different things today. We're going to look at the relationship between mass and weight and what the difference is between those two. Mass and weight will no longer be an interchangeable word. They now mean different things in our physics world. Okay, mass and weight now mean two very different things. And we're going to look at actual weight and apparent weight. So there's a couple different things we're going to talk about today with weight. Okay, so the weight force, or otherwise known as the force due to gravity, is our F sub g. Okay, so if I ask for something's weight, that means I'm asking you to solve for F sub g. Okay, and weight is now in newtons. So weight is in newtons, mass is in what unit? Kilograms. Good. So those are two big clues for you. If it says an object weighs 40 newtons, that means it's given you the force of gravity. It's given you F sub g. It's not giving you its mass, it's giving you F sub g. Okay? And if we use Newton's second law, we can derive it to make F sub g equal to mass times gravity. So here's our equation now for F sub g. This is one that you will use a lot. Okay, so put a star by that one or circle it or something, but mass times gravity, mass times 9.8 gives you an object's weight. Okay, and we use m times g because g is the acceleration due to gravity. Okay, g is equal to 9.8 meters per second squared. The reason here that we don't plug in negative 9.8 meters per second squared is because on every free body diagram and every net force equation we do, we take minus F sub g. We subtract F sub g out, which means we're accounting for the negative in our net force equation, okay, instead of in our acceleration. Does that make sense? Every time we do a net force equation, we take either right forces minus left or upward forces minus down. Since force due to gravity is always acting in the downward direction, we're always going to subtract it out, which means we account for that negative. So mass here is in kilograms. G is in meters per second squared. So you're always going to take mass times 9.8 for anything that's on the earth. Okay? Not negative 9.8 because on all of our net force equations, we're going to subtract out F sub g because it's going down. Right, we're always going to take upward forces minus downward forces, and we subtract it. That negative is accounting for negative 9.8 because we subtract out the gravitational force. Okay, so we plug in positive 9.8 for this one. Forces are never negative. Remember, the negative only indicates the direction. So we just keep our forces positive, and the negative is going to tell us it's going in the downward direction. Okay? All right, so if I ask you for something's weight, that means I'm asking you to calculate its mass times gravity. Okay, or if I tell you its weight is 50 newtons, that means you're going to take 50 newtons equals mass times 9.8. Okay, weight is in newtons, mass is in kilograms. So let's try this. We place a watermelon on a spring scale at the supermarket. If the mass is 4 kilograms, what's the reading on the scale? Okay, and the reading on the scale is its weight. We want to find its weight. Okay, and it's in newtons. We're not going to convert these to pounds or anything like that. We're going to leave it in newtons. Okay, the way a spring scale works is you hang something from that spring scale. So the only force that's acting on our object is F sub g. And that's the only force we have that's acting on our object. So if we want to solve for F sub g, how do we go about doing that? Mm-hmm. Good, times 9.8. So we're going to take mass times gravity. Fg is always equal to m times g. That's one that you'll use all the time, so that's one you got to be good at, okay? Be used to using that. Mass times gravity. Okay, so that means the weight of our watermelon is equal to 39.2 newtons. Okay, do we agree? 39.2? Perfect. Remember, weight and mass are two very different things now. So weight has to be in newtons. Mass is in kilograms. So whenever we say weight, you should think F sub G. Okay, or if it says it weighs this much. Weight, you have to think F sub G. And F sub G means mass times gravity. Something called apparent weight. Okay? Apparent weight. So go ahead and get this kind of written down in your own words, and then I will talk about it, and then I want you to read a little excerpt from the book about apparent weight. So apparent weight gives us a little bit better idea of what our weight would be if we're not at rest. If we're not at equilibrium on the surface of the earth, apparent weight gives us a little better idea as if we're accelerating upward or if we're moving downward, we've got a different weight, right? That's when they call, if you free fall in an elevator, have you ever heard that you're weightlessness, right? If you're weightless, if you're free falling in an elevator, for some reason always in an elevator. Okay, if you're free falling, you're said to be weightless, okay? But that's because the normal force that's exerted on you is much, much, much less. It's much diminished, okay? So if you're riding upward in an elevator, the floor is having to push on you harder, which means the scale is pushing on you harder to keep you at equilibrium. If you're accelerating in a downward direction, that means it's taking some pressure off that scale, which means you're having a lower scale reading, okay? So we're going to do some calculations with our apparent weight on a scale in an elevator. Okay, so this is on page 99 if you want to follow along. I tweaked the question just a little bit, so it might be a little bit different order than what your book says, but we're going to solve this problem. It just happens to be in the book, okay? Your mass is 75 kilograms. You're standing on a bathroom scale in an elevator. Starting from rest, the elevator accelerates upward at 2 meters per second squared. What's the reading on the scale? Okay, and we want the reading on the scale in newtons. Okay, we want to find out what the scale would read in newtons. We don't want it in pounds or anything like that. We want newtons. Okay, so get written down what you need to, and then we'll start with our free body diagram here. So standing in our elevator, we've got two forces acting on us. Rose, give me one of our forces. Gravity, good. F sub G. And what's our other force, Caitlin? Not friction. Going in the upward direction. Yep. Could be the normal, could be the scale, could be the spring, whatever you want to call it, but it's the scale pushing up on us. So you can call it the normal force, you can call it the spring force, the scale force, whatever you want to name that is fine, but it goes in the upward direction. Okay, I'll just call it F sub n for normal. Okay, because we're standing on a surface, that surface is exerting a force upward on us, so I just call it the normal. Okay? All right, our acceleration, is it going in the upward or the downward direction? Upward. So which of my vectors should be longer? My upward force or my downward force? My upward vector should be longer. Good. Okay, so I tried to draw it a little bit like that. Now, we've got our free body diagram. Next step is to do your net force equation. Okay, net force equation. So we're going to take F net is equal to upward forces minus downward forces. Upward forces minus downward, so F sub n minus F sub g. On the same page right there? Okay. Which of these forces are we solving for? The net force, the normal force, or the gravitational force? Which is our overall goal that we're solving for here? The normal force. We're trying to find out what the scale will read, and the scale's reading will be this force right here. Okay? So we're solving for that. So that gets to stay the same. So F sub n. How can we substitute out F sub g? Mass times gravity. So mg. And how can we substitute out F net? What is F net equal to? Mass times acceleration, ma. Okay. Now, you could solve for these separately and then bring them back to the net force equation. I think that it's better for you to be able to see it all in one place first before you start plugging in numbers. Okay. But that's up to you. If you can solve for F sub g first, then just plug in the number. That's fine with me. But I think it's better to have all the variables in and then we start plugging in. So we're going to take 75 times our acceleration. Is our acceleration up or down? Up, so it needs to stay a positive 2. We're solving for F sub n. We'll take 75 times 9.8. Okay? And this minus right here accounts for our negative gravity all the time. So we just plug in a positive 9.8 because this minus, this subtraction right here, accounts for gravity going in the downward direction. Okay, do we agree? 885 newtons? Okay, good. So this was accelerating in the upward direction at 2 meters per second squared. Let's consider what would it be is this reading greater than, less than, or equal to what the scale would read if our system was at rest? So when we were accelerating upward at 2 meters per second squared, we had a reading of 885 newtons. How does that compare to if the system was at rest, if our elevator wasn't moving? It's greater than, right? It's greater than. It's greater than. Do we see why? Kinda? Okay, let me just go through the math really quickly so that you can see it, okay? If you want to put this in your notes, that's great. If you want to just watch along while I do it, that's fine too. If my system is at rest, my system is at rest, that means I've still got a gravitational force, I've still got a normal force. But if my system is at rest, what's my net force when my system's at rest? What's my net force equal to? 0. Which means F sub g is equal to our normal force. F sub g is equal to F sub n, which means I'm going to take 75 times 9.8 to find that scale reading. And that's going to give me a normal force or a scale reading of 735 newtons. Okay, so that's the reading that the scale would give when it's at rest. So we were right. When it accelerates in the upward direction, the scale has to exert a greater force, which was 885 newtons. Okay? We agree? We see why that works? Okay, this last one I want you to do on your own. What would the scale reading be if the elevator were accelerating downward at 2 meters per second squared? Okay, so as I walk around, I want to see your free body diagram. I want to see your net force equation along with your final answer. Okay, so I want to see all the work that goes into this. Okay, so our F net equation here ended up (75 kilograms times -2 equals F sub n minus 75 times 9.8, which gives us a scale reading of 585 newtons. So less than, equal to, or greater than our at-rest system. Less than, right? Because as I'm accelerating downward in an elevator, it's taking some pressure off that normal force. Okay, and it's not having to exert such a great force up on me in the upward direction. On Earth, a scale shows that you weigh 585 newtons. What is your mass? So when we see the word weigh or weight, what should we automatically think of? F sub g. We should automatically think F sub g. And we know that F sub g is equal to mass times gravity. So whenever we see the word weight, and our unit is newtons, we have to think F sub g. That's very important. And when it's in newtons already, that means that is our force. All right, Bree, tell me what you had. 59.7 kilograms. Very good. Mass is in kilograms. Okay, to get that mass by itself, we're going to divide over our 9.8. Okay, very good. So now I want you to keep this mass in mind. We've got a mass of 59.7 kilograms. Then I want you to answer, what would the scale read if I was on the moon and I had a different acceleration due to gravity? So do I lose any mass particles when I go to the moon? No. My gravity changes, which means my apparent weight changes. So we're going to use the same mass you just solved for to find our weight, or what our scale would read, which is our weight. F sub g on the moon, still mass times gravity. This g variable just changes. Okay, what was our weight or our apparent weight on the moon? Cole, what'd you have?
95.51 newtons.
Good, 95.51 newtons. Very good. Okay, how do we feel about net force, solving for net force, building our equation, building our free body diagram? Feeling pretty good so far? Okay, we know how to solve for weight, F sub g. Okay, we've got just a couple different little topics to cover really quickly. Something called the drag force. This is a different type of force, and we usually think of it as the air resistance force. Okay, this is a force that's exerted by a fluid when something's moving through that fluid. So anytime it's not resting on a surface, if it's moving through the air, moving through the water, right? Swimmers experience a lot of drag force. Race car drivers experience drag force in the form of air resistance. Okay, we use air resistance more than we'll use drag in the water or anything like that, but air resistance is a major type of drag force. Okay, and to build on our air resistance force just a little bit. So terminal velocity is a velocity that's reached when our air resistance force equals our gravitational force. When we reach a state of constant velocity, okay, that we call terminal velocity. It's reached its final and fastest speed. Okay, so anything that's moving at terminal velocity means it's moving at constant velocity, which means its net force is equal to 0. So I just want you to think about this question up here on the board. Which is going to reach its terminal velocity faster, okay, in a quicker time frame? Is it going to be a compact, heavy object, or is it going to be a light object with lots of surface area? Which would reach its final velocity faster, or in a shorter period of time? What do you think? If I take a paper ball that's rolled up or a sheet of paper and I drop both of them, which do you think will stop accelerating first? The sheet, right? My sheet has much more surface area, which means it allows for air resistance force to push up on it in multiple places. Okay? So as I drop both of these objects, my paper ball will continue to accelerate as it falls down for a longer period of time. My sheet of paper will accelerate at the beginning, and then eventually it will reach a point where it stops accelerating and it just falls at a constant speed. Okay? Once it reaches that place at which it stops gaining speed and it stops accelerating, we call that terminal velocity. Okay? And I'm going to have you watch a video to explain terminal velocity a little bit better and give you kind of a visual about it. So if you open up your Chromebooks, you need your Chromebooks and your headphones that you brought today. Did I tell you guys to bring headphones?
Yes.
Okay, good.